Cluster Builder and Space Scotland webinar, considering the role for biotechnology in space. My name is Kim Cameron. I'm part of the business engagement team at the Industrial Biotechnology Innovation Centre, and I'm delighted to host this morning's session alongside Christina MacLeod from Space Scotland. So we have a packed session for you this morning. We'll be together for around 2.5 hours. And taking a look at our agenda, I'll shortly run through some housekeeping, and then I'll give you an introduction to the Bioeconomy Cluster Builder project. Then I'll hand over to Christina for some background to Space Scotland, and then we'll hear from the first of our guest speakers. After the first presentation and discussion, we'll take a short comfort break, and then we'll continue with the remainder of the webinar. So some housekeeping. Everyone's will be muted throughout the webinar, so please use the Q&A box for any questions that you'd like to put to the speakers or to any of us from the BCB or from Space Scotland. And you can use the chat if you have any technical issues or any wider queries. We'll be recording today's session, and a copy of the recording will be posted to the BCB website shortly after the session runs. And you can find, I'll give you the BCB web address shortly. So an introduction to the Bioeconomy Cluster Builder. It's an ongoing collaboration between the Industrial Biotechnology Innovation Centre and Innovate UK KTN. We're now in our 4th year, and the project has three broad aims. The first being to raise awareness of the different applications of biotechnology. The second is all about connecting people and resources to support the development of new and existing value chains using biotechnology. And the third is to encourage the utilisation of Scotland's bioresources, essentially the raw materials that arise across the country that can be used as feedstocks for biotechnology processes. And so one of the main ways in which we raise awareness and make these connections is through the delivery of events. So far, the project's delivered 36 events with a combined audience of around 3,250 attendees. And one of the exciting things about being part of the Bioeconomy Cluster Builder is the wide range of sectors that we engage with, and today is a good example of that. And in the past, we've worked with the textiles industry, construction, agri-food and forestry in the development of events. And as I mentioned, we're recording today's event, and recordings of all of our past events over the last 4 years are available on the Bioeconomy Cluster Builder website, and the address is there in the bottom left-hand corner of the screen. We also offer a range of other support services in addition to running these events. We have access to the partner organisation networks and technical support. So both the Industrial Biotechnology Innovation Centre and Innovate UK KTN have an extensive network of stakeholders that we can tap into. And we leverage these connections to run targeted focus groups and roundtables, bringing together stakeholders to help organisations move forward and progress their at the application of biotechnology in their manufacturing processes. And we offer support and guidance in accessing a range of funding and investment opportunities. And as I mentioned earlier, we can help with access to potential feedstock supplies. So we have a tool within the Innovation Centre, which was developed in conjunction with Zero Waste Scotland and Scottish Enterprise, from which we can produce bespoke reports about the locations and quantities of bio-based materials that can be used as feedstocks for biotech processes. So please do engage with us if you'd like support at all. Keep an eye out for our events, and send people our way. You can see my contact details on the screen here, along with the Bioeconomy Cluster Builder website. And we're also on LinkedIn if you want to follow us there. Our next event's on the 22nd of February. This is an online event, again, looking at applications of biotechnology to develop a circular textiles industry, particularly looking at end-of-life textiles. And we're running this in collaboration with the Innovate UK KTN SUSBio programme. You can find details of it on our website, or you can access it using the QR code there in the bottom right-hand corner of the screen. And lastly, a plug for the forthcoming iBioIC conference next month, which will be held in Glasgow. This is our 10th anniversary conference, and looking at the theme will be the transformation of the biotechnology landscape. So looking back at progress over the last 10 years, and then looking ahead to the exciting developments we see coming down the pipeline in the future. So there'll be sessions, workshops, networking opportunities, exhibition spaces, and a civic reception. And the conference is the focal point of Scottish Bioeconomy Week, which runs that whole week commencing 11th of March. Registration's open now. There are also a range of sponsorship and exhibition opportunities. You can find out more about those using the QR code here or the web address at the bottom of the screen. So that's enough for me for now. I'll hand over to Christina, who's going to give you a bit of background to Space Scotland, and then we'll hear from the first of our focus session speakers. So Christina, I'll stop sharing and you want to go ahead?
Perfect. Thanks very much, Kim, for kicking us off. Just wondering, can everyone see my screen all right? Looking to you, Kim.
Yep, all good, Christina.
Lovely. Well, very lovely to be here. Thank you so much to the team at iBioIC for helping make this event such a big success. We've got a great audience from all around the world, really exciting to see. So thank you very much for your time here today. I'll try to keep this quick, just give you a bit of an overview of what Space Scotland is, a little bit more about why we're doing this, and also introduce us to our panelists. So yes, I'm Christina McLeod. So I am the Cluster Development Project Manager at Space Scotland, and you'll find out what that means in just a moment. But for those of you who have not engaged with us before, I've put together a few slides to let you know who we are. So we are a collaborative voice for the Scottish space sector, who are looking to promote Scottish space sector interests and essentially create a more well-rounded, flourishing space sector and also promote what's going on just now. So we aim to form a community of Scottish businesses and link together industry, academia, and government to raise the profile of the space sector here and also establish new business opportunities. So we work with a really collaborative and fantastic community, and that's kind of where this work stems from. So essentially, the Scottish Space Cluster is quite complex, so we've got quite a few moving parts. Scotland, so while there are clusters all over England, Wales, Northern Ireland, Scotland is kind of this meta cluster where we've got loads of activities going around all over the country. So we've got quite a strong cluster on the North Coast with some of the spaceports, Prestwick as well. We've got Edinburgh, Glasgow, and Dundee. And so essentially there are all these different kind of areas that are kind of specialized in different things, and we kind of are seeking to unite them through Space Scotland. And so we work with government and academia to help make this happen. And so just to put it into context, excuse me, so this is a bit of a, I guess, a little puzzle because it's Scotland from above. So you can see Shetland here, the northern tip, and then this is the rest of Scotland down here. And so you can see there are huge areas of activity here around the central belt, and then up into Fife and into Dundee. And then you've got Aberdeen, and then you've got some activity here along the north coast. And so you can see there are a few circles on the map, and those are our spaceports. So here at the northern tip, we've got Saxford, we've got Sutherland Space Centre, we've got Spaceport 1, we've got Machrihanish Air Base, and then we've got Prestwick. And so most of these are vertical launch sites, but a few of them, so namely Prestwick, are horizontal. So we've got a lot of activity going around in Scotland, very exciting, but as you can see, everything's quite spread out. And so that's what Space Scotland seeks to do, just to unite all these different activities going on. And so just to give you a very quick whistle-stop tour of the Scottish space sector, this is a little bit outdated now, but we've got over 130 Scottish space organisations, and we're currently mapping to get a more accurate figure. So that's going on right now with another project. And actually Scotland has the most space sector employees outside of London and the southeast. And so the space sector is growing at such a huge rate. We've got a very diverse range of organisations all across Scotland. And so overall, it's just a really exciting sector to be in. I actually think we're almost up to 8,600 employees now. So you can see how much that's grown in the past few years. And so the Scottish value chain, essentially here, we've got small sats. So originally there was a lot of activity going on in Glasgow, who were pioneers in kind of that small sat revolution. And then we've got our launch services that I ran you through in the previous slide. We've got launch vehicles, we've got downstream, and we've got future new applications and payloads, component subsystem supply and space exploration. So we've got a huge range of expertise all over Scotland. And I think there are a few maps and kind of lists of different companies that are doing activities. If I had time to go through them, I would. But yeah, if you want to ask about any of those companies, let me know and I can provide you with more links. But I just really want to show to you how wide and broad the space sector is here, because there are over 130 space companies operating in the country. So overall, really exciting space to be in. And so this all ties into Scotland's space strategy. And so we are looking to grow the space sector in Scotland, an increase in workforce, a larger annual contribution to the Scottish economy, and also looking to launch. So there's news that we're going to have our first launch out of Scotland this year, but also supporting all our other activities that are going on and looking into kind of new and emerging markets and opportunities, such as the discussions that we're about to have today. And so a little bit more about what I specifically do. So I mentioned that I'm the cluster development project manager, and essentially I am working here to basically build the profile of the Scottish space sector by running quite a few activities across these different areas. And so the UK Space Agency launched the cluster funding program just over a year ago now to support local growth in the region. So it basically provides each of the regions around the UK with their own pots of money to basically conduct activities as they see fit. And so we decided that the top 3 priorities for Scotland would be sustainable space, workforce development, and knowledge exchange and cross-sector diversification. So under these work packages, we've got a huge range of activity. We've got 15 different projects, and underneath each of these projects, there's a whole range of activities. So there's a lot of really exciting work going on just now, and these are all very broad topics, but we're doing stuff such as, conducting carbon audits for space companies around Scotland, sending satellite kits to underrepresented areas around Scotland. And then with our knowledge exchange and cross-sector diversification, got a bit of a list here of what we're doing. So we're working with other sectors to try and find opportunities for collaboration, basically link people up, link businesses up, create more opportunities, and just engage more with other sectors, because everyone's doing such fantastic work. And I know I've learned a lot through the iBioIC guys through speaking with them and planning this event. So overall, just really exciting activities. And we've already run our Space Data for Financial Services Accelerator, and now both our Agriculture Knowledge Exchange Consortium and with this event, the Biotech Knowledge Exchange Consortium is now officially started. So the other accelerators are coming up, but we've just got a huge range of activity. And this is basically the first biotech event that we are doing. So we're very excited to be here today. And so I think I've probably told you enough time, but yeah, the space sector here in Scotland is incredible. We've got a great startup community environment. We've got access to government, academia, and industry through our Space Scotland group, and just a very vibrant ecosystem of new as well as established businesses. And so that's it for me. I'm very keen to start the discussion with panelists. So thank you very much. If you have any questions, please feel free to pop it in the chat. I didn't pop my email in here, but I'll put it in the chat once I stop sharing my screen. And feel free to reach out if you're keen to speak more about what Scotland has to offer, what Space Scotland is looking to do, or just any general questions. So thank you very much. Now I'm very excited to introduce our first speaker, Michael. We are very keen to have him today. So I will let you do your intro. Don't want to take up too much time, but and then afterwards I will come back on the screen and explain to you how we're going to field the questions. So over to you, Michael.
Hi, thanks, Christina, and hello, everyone. It's a real pleasure to be speaking here today. I'm just going to pop up a presentation, which I hope everyone will be able to see. So today I'm going to talk a little bit about human health in space. We'll be discussing the roles of biotech in maintaining human health in space. We'll have a talk about where we are now, where humanity's exploration of space is going in the near future, and something about the barriers to achieving extended long duration space exploration. As Christina said, I'm Michael Morn. I'm founding director at Max SciTech. Just a little bit about us. We're a scientific research and development company. We've got links with UK research establishments. We're a member at University of Durham's Orbit Research Facility at Net Park in County Durham. And we've got a wide experience over the years in a variety of sectors, but most specific to today and most recently, we're working on a project part funded by the UK Space Agency around closed loop life support systems, specifically for breathing gas generation. Alongside that, we have a good deal of interest and experience around biotech, agritech, medtech, but specifically interest towards applications in the space sector. So, as I said, excuse me, I've gone the wrong. So as I said, we're going to talk about where are we with relation to space exploration at the moment. Well, currently, all space exploration, human space exploration, is low Earth orbit. So we've got two space stations currently in LEO, the International Space Station and the Chinese Tiangong Space Station. For this kind of mission, resupply and astronaut return is relatively easy. You're a few hundred miles away from Earth. Transit times can be in the hours. That said, resupply costs can be expensive, and I found a figure of $22,000 a kilogram from SpaceX for resupplying the International Space Station. So though we do have facilities for resupply, they can be expensive, and there are benefits to looking at things like recycling and limiting resupply, but the very short mission durations and in terms of resupply, I know we've had astronauts in space for over a year now, but resupply missions are typically no more than a couple of months apart. So the challenges associated with low Earth orbit and space stations are very different to the extended duration space exploration that we may see in the coming years and decades. So planned exploration missions, as I said, LEO, we've got the ISS and the Chinese space station. The ISS is due to be decommissioned by 2030. That may extend a little bit. However, we have a number of commercial space stations, LEO space stations that are being planned and built at the moment, notably Axiom, Sierra Space, are probably some you may have heard of in the media, amongst several others. And what we're going to see in the next few years, I believe Axiom will have their first habitation units up there by 2027. So in the next few years, we're going to see commercial areas in space where experimentation, space tourism, and trips to space are going to become more common, but again, all in LEO. Lunar exploration, we have had people on the moon before, but you may or may not have heard of the Artemis project, which is a collaborative mission between NASA, the Japanese Space Agency, European Space Agency, and the Canadian Space Agency. And the aim there is to put people back on the moon by 2030. And this is going to include not only an orbital habitation module, but also a lunar surface moon base, essentially. And a lot of the technology around life support hasn't been implemented yet, and it's still in development. So there are opportunities and also requirements in order to facilitate the successful completion of Artemis. And this is all happening this decade. You know, we're looking in the next six or 7 years. Mars, we've all sort of seen the movies. Mars is a little bit further away, a little bit more of a challenge, but the SpaceX notably are currently developing launch hardware to facilitate Mars transit and looking at the technology to facilitate human habitation on Mars. The challenges associated with this type of deep space exploration, your resupply is more challenging, if impossible, and your return to Earth is more challenging for astronauts and for materials. So if we're looking at the barriers to longer duration exploration, as I say, we've got the technology now. We can go to the moon. SpaceX's Starship, NASA's SLS, China's Long March rocket. We have the technology to launch to the moon, and we have habitation units that are already in use or have been in development across the world. So we've got space station technology. However, we have at the moment, we're working on with life support on the basis of regular resupply. So we've got established systems in LEO space stations, but they're relying on regular resupply of food, water, atmospheric gases, pharmaceuticals, and also medical evacuation for astronauts. Longer duration, we're going to have to handle all of these points that I've raised above. Additionally, in implementing recycling to reduce payload requirements and to reduce the frequency of resupply missions. So we've got a lot of challenges to overcome, even though we can get people into space and we can keep them safe to enable deeper space exploration. There's a lot of work to do. So maintaining life support systems, as I said, we've got several things we need to consider here. Breathing gases, that's something that's quite close to work that we're doing at the moment. Sanitation, waste handling. As biotech companies, these are all things that we're probably touching on processes that you're familiar with here. Water recycling, diets, nutrients, vitamins, proteins. I mentioned here in situ resource utilization as well. Is there any way that we can start using resources when we're out in space? And there are examples of that through biotech and agritech. Growing vegetables in lunar regolith, for example, might be an option. But one thing we need to recognize is having life support systems that keep astronauts alive is one thing. We also have health considerations, so we need to ensure that the welfare of our astronauts going forward, and a lot of these a lot of the effects of extended duration in space and in microgravity are understood. But there's a lot of work to be done in order to better understand and mitigate the effects of long duration space exploration. So all of these things that I've listed: muscular atrophy, so we'll see muscle wastage, the psychosocial implications, that's the implications of being in isolation on a long duration space exploration, changes to the cardiovascular system, your immune system, exposure to radiation. We're also got challenges like medical diagnostics and medical treatment in space. Now, these are things that are being investigated at the moment, but as a lot of you will no doubt be aware, that medical diagnostics that are commonly used on Earth may not be applicable for zero gravity or microgravity environments. So that there's development to be done around diagnostics and treatment. One thing we recognize, that the main slant on our project is very much chemtech and hardware, but we do recognize that a holistic approach is going to be required here, and that it's not a single answer to the problems. We're trying to replicate a lot of the processes that happen here on Earth, and I get asked by people when we talk about reactors for processing breathing gases, and they say, well, why don't we just bring plants with us? Well, the plants are going to be a part of this, but the reality is it's going to be a holistic. It's going to be an interface between biotech, chemtech, agritech, and engineering that allows us to facilitate this type of long duration exploration. I've put up here, and this is probably one to screenshot. I'll not go through them all, but this last year I was involved in the European Space Agency's harmonization process, where they were looking at actors within life support, and I picked out through hard work and searching people and institutions that were working within life support. What we're keen to see is a platform for actors within life support technology and astronaut welfare to be able to come together and talk about what they're doing, and also talk about the opportunities and the requirements for longer duration space exploration for astronaut welfare, and to stimulate collaboration. So as I say, this is a non-exhaustive list, and if you feel like you should be on there and aren't, these are things that we really need to sort of bring together in this sector. I think is a good understanding of who's doing what around the UK. As I said, we've had experience in a range of sectors, and I wanted to share a little bit our journey into the space sector. We began developing technology back in 2020, so we're relatively new to the space sector, and I just wanted to introduce here, for those who aren't familiar, or even for those who are already acting in the space sector, some routes into accessing opportunities. The UK Space Agency is leading a couple of accelerator programs every year. We were lucky enough to be involved in the LEO and GEO, the inaugural accelerator programs, but keep an eye on the UK Space Accelerator website, or on the Space Agency website. There were established companies as well as newbies to the space sector, and it was really good grounding in the legal framework and the sector in general, and essentially accessing opportunities within space. The catapults and clusters, Christina already mentioned the Space Scotland and space clusters. There are clusters around the country. It's worth reaching out if you're interested in getting more involved in the space sector. Dedicated space exploration and science teams at the UK Space Agency. So there's an exploration team. There is apparently a new front door approach coming. I don't know when that's coming online, but keep an eye on the UK Space Agency's website if you're looking to engage with them. Really, if you're looking to engage in the European Space Agency in tendering for work, the European Space Agency is the place to go, and it's worthwhile keeping an eye on the ESA website. So the ESA Star website is a platform for ESA to publish tenders and intentions to tender, so you can see what work European Space Agency are looking to tender for in the future, and what's available at the moment. In terms of engaging with the European Space Agency, they have business ambassadors across the country again, so you'll have a local ESA business ambassador. If you jump on the business.esa website, you'll be able to find out who your local ESA ambassador is. The European Space Agency is also running bid tendering workshops, and I believe there's one that's just been announced. So again, it's worth having a look on the UKSA or the ESA website about bid tendering workshops, which will give you a little bit more information about how to engage with the European Space Agency and what their requirements are. And ESA will be key to Artemis, so if you are interested in being involved in the life support technology going forward, it's worth a look. Space funding, again, we, as I said, we're lucky enough to gain funding from the UK Space Agency. So we're currently running a part-funded project. Funding opportunities can be found through the Space Agency website. Additionally, the European Space Agency General Support Technology Programme is always open and accessible through the UK Space Agency, who have a dedicated department for that. And OSIP, relatively new open space innovation platform. But if you jump on the ideas.esa website, that'll tell you a little bit more about that. The Department for International Trade, a lot of this work's happening in the United States. The Department for International Trade has a dedicated space team as well, if you're interested in knowing more about working across the pond. As well as the life support, which is at the core of what we're doing, I just wanted to mention a couple of other market opportunities, essentially, and what's happening, or what is expected to happen in these new and emerging markets. So traditionally, the space sector markets have been around data, satellites, GPS, Earth monitoring, has been where the bulk of the space markets has lain in the past. What we've got coming up now, as I mentioned, LEO space tourism. So we've got a number of companies, Axiom, I believe the Hilton signed a deal for a space hotel, which we may see in the not too distant future. So what was a relatively small market is projected to grow quite significantly by 2028. So there is opportunity there, but there are also requirements to facilitate that kind of space tourism in astronaut welfare and in tourist welfare, space tourist welfare. Lunar stations and habitation, I mentioned the Artemis. There's a lot of budget to go on that, and the life support systems haven't been defined fully yet. We're looking at space agritech, space medtech, space diagnostics. These are all things I mentioned around astronaut welfare, and also emerging at the moment in orbit manufacturing. And this may be relevant to some of the people on the event today, pharmaceuticals. So if we're looking at building things in space, we're going to have more platforms for that, not only orbital space stations, but also orbital manufacturing platforms where we may be looking at manufacturing high value materials which are not accessible here on Earth in Earth gravity. So pharmaceuticals, formulation, tissue culture, and organ growth are all things we might expect to see in the coming years as markets which are to be exploited. I'm just going to go on now after that sort of whistle-stop tour of astronaut health and talk a little bit about what we're doing, and I'll not dwell too long on this. We mentioned recycling. We mentioned the importance of reducing payload in terms of enabling space exploration, and that's at the heart of what we're trying to achieve, is to recycle water primarily as part of a breathing gas system. So at the moment, we generate oxygen from water by electrolysis. Originally, the hydrogen and the carbon dioxide, which were waste products from astronaut respiration and electrolysis, were vented into space. More recently, closed-loop life support systems can recycle, with state-of-the-art technology, about 50% of the water. We're looking at implementing a system that can recycle up to 100% of the water, but also give us a platform for producing useful materials, polymers, fuels, fertilizers, things that may be important in lunar exploration and beyond. And to put this into context, each of us would breathe a kilo of carbon dioxide a day. It amounts to about 200 to 300 kilograms of water a year just to breathe, and that's around about £5.5 million in resupply just to LEO. And we did do a sort of back of the envelope calculation on current costs. If you were going to take all the water you needed to breathe to Mars with you, every breath would cost about £70. Obviously, we're not going to do that, but it does highlight the requirement for recycling. And as you can see on the screen here, though we've got chemtech, we've got engineering in there, we're also going to be relying heavily on biotech for our waste recycling and to feed into this whole closed loop system that I have. It brings me to the end of a kind of a whistle-stop tour of astronaut health and the market as we see it at the moment. So I'm happy to hand it over now to the floor if there are any questions, and I hope this has sparked some interest, some thought, and maybe can spark some further conversations around opportunities in this sector. Thanks very much.
Great, thank you so much, Michael. That was really, really interesting and a really great talk to kick off our discussions today. I know we've had a few questions come into the chat. We've got about 25 minutes, so really keen to see if you have any questions. Feel free to pop them in the Q&A chat. And just now to let you know, the normal chat is currently not working for participants, so we're just working on getting that fixed just now, so apologies for that. But first question to kick us off. So Michael from Esther, who has asked, a lot of discussion is about establishing a human base on the moon and Mars, but most forget that we also need to figure out how we can get astronauts to Mars. Are you also focused on crew safety during the almost 3-year-long return flight?
Yeah, so now, first thing I'll say is that specifically the work that we are doing is looking at facilitating the longer duration space exploration. So looking at how we can start to close the loop in terms of resource usage, and specifically for us, we're looking at breathing gases. We're looking at saving water. Now, in terms of and you draw a very good distinction there between the facilitation of space exploration and the responsibilities that we have to ensure that the astronauts are safe. The technology that we're developing is designed to operate in LEO and low Earth orbit, as well as in Mars transit, and also for us, designed to be able to begin to process the Martian atmosphere when we arrive. So the in situ resource utilization. So we're hoping to offer a process which is designed and not only with LEO, Lunar, and Mars transit, but also Mars habitat in mind. But as I said, there's a lot more to space travel than simply generating oxygen and making sure people have got water. We personally aren't doing a lot of work towards that, but I know that there is a lot of investigation going into the minimization of the effects of radiation and longer duration transit away from a protective environment, essentially. So I can't talk too specifically about it from our own work point of view, but it is a real consideration, and this is where we come more from the point of view of astronaut welfare than life support, because it really needs to be considered. I think there is I can't remember the exact figure, but I think there's an understanding that for every period spent outside of the Earth's magnetic field and in direct solar radiation, the astronauts' life expectancy is decreased by a certain amount. So that needs to be taken into account. So yeah, we can talk in general about coatings and things like that people are putting on or people are investigating to help absorb cosmic rays and solar radiation, but it needs to be considered.
Great, thank you very much. Really interesting. Yeah, I don't really have much of a background on any of this at all, so it's all really fascinating. So yeah, I can see questions also streaming in. So yeah, thanks Esther for that question to kick us off. Another one, so this is from an anonymous attendee who's wondering, do you see any competitive edge that the UK or Scotland can bring to crewed missions compared to leveraging UK expertise in robotics and uncrewed missions? Why not? I'll stop there and then ask the second part of that question.
Right, yeah. I mean, we were, as I say, we got involved in the harmonization process with the European Space Agency last year with relation to life support technologies. And what surprised me a lot was the lack of exposure for research groups and companies that were operating in the life support and astronaut welfare in this type of research. So one thing I'd say is that yes, I do believe that the UK has a role to play in this, but I also believe the UK is already playing a role in this. And what we need to do as a country, certainly within the European Space Agency, is put our hands up and ensure that we are recognised, and where the work that's done in the UK is advertised overseas. And part of what I mentioned about going to the ESA Star website, not only do they offer tender opportunities through ESA Star, but they also have a Connect service. So if you have if you have a skill set or a product or a service that you offer, there's a facility for you to advertise that through ESA by posting your business details there, and that will facilitate agencies or primes or other companies who are looking to act in this kind of sector to find you. So in terms of the distinction between that and robotic space exploration, I know that the UK is doing a lot in robotic space exploration. So in terms of rovers and in terms of satellite technology, in terms of orbital debris removal, we've got a lot of people working here, and we probably know a lot more about them than we do about the groups who are working towards biotech or chemtech or medtech solutions for astronaut welfare in space. So the two different fields, but I think we're operating in both of them at the moment. But I think what we need to do in the UK is to kind of bring these actors together and shout about it so people know what we're doing. Yeah.
Great, thank you very much, Michael. There's also a second part to that question, just around, what are we looking at biotechnology from space as a way to promote terrestrial applications? So anything in your worker system kind of apply to that?
Yeah, I mean, absolutely. With the upstream and downstream transfer of technology from space is really important. One thing you will find that the market for life support technology in space at the moment is very limited. This will increase as we go forward, but we've got to keep an eye on what we're doing, the terrestrial applications for what we're doing in space, as well as has always happened, the applications for terrestrial technology in space. So I guess there are a few ways of looking at this. We can look at things like in-orbit manufacturing, where we might be making things in space in a orbital manufacturing platform, specifically for bringing back to Earth. And as I mentioned, tissue growth. It could be organ growth, tissue cultures. It could be pharmaceutical formulations. We could be looking at different formulations of existing pharmaceuticals. So there's definitely an application or a potential application for in-orbit manufacturing to benefit existing markets here on Earth and to benefit people here on Earth. But yes, there will certainly be a reflection down from technology that's being developed in space, bioreactors, for example, waste management, all of these things that are done in space, they need to be done in deployable, robust, and efficient in an efficient manner. And all of those things are relevant here on Earth. So if we're looking at waste management, there'll be applications there. If we're looking at bioreactors for producing food, for producing nutrients or vitamins, again, there are obvious mirrors here on Earth. So yeah, that's always got to be in the focus. Similarly, for our technology, we're processing carbon dioxide in space, but we've got a very clear eye on the applications for processing carbon dioxide and making useful things out of it, and dealing with carbon dioxide emissions here on Earth. So yeah, there's always that reflection.
Great, thank you very much, Michael. And also there was just another quick question, a technical question. So with the closed ECLSS, it's possible to keep the CO2 level below 1% instead of 3%.
There are various technologies, and again we talk about upstream and downstream or on-Earth technologies applying in space. There are various exposure limits depending on how long you expect to be in a certain breathing environment. So you might find, for example, if you're looking at extravehicular activities, your carbon dioxide levels may be acceptable carbon dioxide levels may be a lot higher. You may be looking at 5% or potentially more for short durations. The actual ppm level, the carbon dioxide level that you end up with in your breathing environment is going to depend on how much energy you put into taking that carbon dioxide out. The more we take out, the lower it gets, the more difficult it is to remove it, but also the technology that we're using to remove the carbon dioxide. And I'm talking about Earth-based applications. So we can look at a direct analogy would be submarine life support, for example. Something that's well established. We've had submarines for a long time, and particularly if we look at longer duration and nuclear submarines, there'll be a good deal of technology transfer into the space sector. That said, the methods for scrubbing carbon dioxide from the atmosphere within a submarine life support may be very different to the methods that they use in the space station. So we've got things like membrane methods, we've got amines, we've got various methods there, all of which have their advantages and their disadvantages. And one thing we've got to bring into the equation again is human health. So we've got to look at whatever we're processing in this gas. What are the risks associated with particulates, with contaminants from your scrubbing agent. So the answer is yes, you can get the carbon dioxide level down as low as you want, but there needs to be a balance between energy use and then between what kind of scrubbing agent you're using and how compatible that is with astronaut welfare and astronaut health. And there's going to be a trade-off. And ultimately, we may find that biotech plays a role in this as well. We may find that some hardware scrubs down to a certain level, and we've got bioreactors which can remove more of the carbon dioxide. But we'll see where that technology moves.
Great, thank you very much, Michael. Yeah, got questions streaming in, so I think we've got about 13 minutes to get through a few more questions, and then I might ask one of my own at the end. But next one is, Michael, where do you see the commercial opportunities for Max Sci-Tech when it comes to LEO and space stations?
Right, yeah. So as I say, we've got space stations at the moment, and payloads costs are coming down. So the benefits of our system to recycling in LEO are probably lower than they may be for lunar or for Mars transit, or for transit to anywhere else in the solar system. Really looking at reduction in payload, the further away we get from Earth, the better. The other thing which I didn't really mention is it all depends on what you want to do with your materials. So one of your options for breathing gases is to take your waste products and turn them into methane and use that as a propellant. So I know there are plans in some of the commercial space stations to use methane as a propellant and oxygen, and our system doesn't lend to that, whereas the existing Sabatier system, which is on the ISS, does. But we may see in the coming years a move away from methane towards ion thrusters, depending on how that technology develops, and also the use of methane may be less attractive as a low grade propellant, as a propellant on Mars for sort of local transport, just due to the challenges of accessing hydrogen on Mars. So what I'd say is that the market may develop to suit in LEO our kind of technology, but I think we're looking further towards lunar and Mars transit and Mars habitation.
Great, thank you very much. Very interesting question there. And so our next one is from Catherine, who has asked, do we think we need more of an understanding of microbial behavior in the space environment before we can move towards their use as support systems in space exploration?
Yes, definitely. There's I mean, there are means for exploring microbial growth and agricultural growth in microgravity environments, through things like random orientation machines, through here on Earth. So we can look at growth processes here on Earth and roughly simulate how growth might happen in microgravity environments, but it's there are differences that are unavoidable compared to actual growth in microgravity environments. So I think what we'll find as orbital experimental platforms become more accessible is that work on microbial growth will change. Microbial, algal, agricultural growth will grow rapidly. If you excuse the pun, you'll get very, very much different groupings of cells, and obviously different ways that cells aggregate in a microgravity environment. So I can't say that you can expect anything that works here on Earth to immediately work up in space. You don't get materials don't move in the same way. Liquid gas separations don't work in the same way. So there's a lot of work to be done, and a lot of work is being done at the moment.
Great, thank you very much. We've got a question in here from Harry, who has asked if you know that if there will be a significant overlap in the potential treatment of muscle atrophy for astronauts and people experiencing this on Earth for more terrestrial reasons, or are the two conditions very different?
It was very recently the Northumbria University announced a program of looking at Earth-based techniques, replicating Earth-based techniques to try to find methods to reduce, I think it was bone density decrease and muscle density decrease. This was only announced in the last sort of month or so, and I'm yet to talk to the guys running the project. But there's a lot of understanding here on Earth about muscle wastage and treatments. I think their technology was based around around things that were implemented for amputees, and building on that. So what I'd say is that there's going to be a link, and people are actively exploring the links between Earth-based treatments and Earth-based exercises for similar conditions and how they might apply in space. So Northumbria universities want to look for on that, and the answer is yes, almost certainly there'll be crossover, and we're going to see more of that happening in the coming years.
Great, thank you very much for that question, Harry, and for your fantastic answer there, Michael. I know we are quickly running out of time. I think we have time for one more question for the audience. So if anyone has one, feel free to send one over. But I'm very curious about how all these different initiatives, you know, that you're working on, kind of can work better together to continue growing the sector. And how does it work currently? You know, how do you see it moving into the future? Things like that. I'm really curious about that.
Yeah, absolutely. So we've been speaking for a while with the UK Space Agency about generating an active working group around astronaut welfare, and I can see how that might includes biotech, agritech, as well as the sort of hardware from life support technology that we're looking at, through to radiation shielding, and all the things we've touched on today. I think it's really important. It was quite surprising to me how little there was no centralized understanding of what the capabilities are within the UK. So I think it's going to be really important for to establish a working group around let's call it astronaut welfare, but all of the things that encompass biotech, so that people can begin to collaborate, understand what's happening, and we can have discussions like this about how the market is emerging, developing, and how the UK can be part of that going forward. So I think it's important, but I don't think there's enough in place at the moment to bring these things together. That said, we've got the clusters, we've got the catapults, we've got the groundwork there for people to come together. So I think it, you know, from our point of view and the clusters point of view, making people aware that this market is emerging, and that it already we already have actors in the UK, and from the biotech companies and from the research groups, it's really sort of reaching out to the clusters and trying to make themselves known.
Yeah, great. Thank you very much. It's really interesting to see your view on that. And so, yeah, from what I understand, you know, we have the groundwork here. So we've got a lot of actors doing all their amazing work, but we just need to centralize it a bit more and connect in with each other a little bit.
Yeah, and events like this really facilitate that. I mentioned, you know, we're a member of another biotech group here in the Northeast, and gave a talk about space last year, and it just it puts it out to people who won't necessarily be familiar with this sector or won't realize that what they're doing is potentially relevant to the sector. So yeah, just getting the information out there about who's doing what and what needs to be done is important.
Yeah, I know we have quite a diverse audience in the chat. So yeah, really keen for them to connect in with you after this event, keep speaking to you, see what opportunities are there. But also, yeah, as I mentioned earlier, I am the cluster development project manager for Scotland. So feel free to come to me. All the clusters all talk to each other as well. So, you know, I'll be speaking about this event to yeah, the cluster that you're in there, Michael, and be really good. I'm also just curious, yeah, how you engage with your local cluster just now, and you know, what you'd suggest to anyone else looking to engage with their cluster, like what support have they offered
Yeah,
you?
so I mean, obviously the clusters are a relatively new thing. There's obviously from my point of view, I have the email address of the people I need to speak to. There are monthly meetings. It's worth looking out for that as well with the Catapult. So our local Catapult does a monthly online meeting, and I've spoken at that a few times. But it's worth sort of dropping in. Dropping into to events, to chats, and also sort of making yourself known. But I think if it was someone who was new to the sector, my first advice would be to find out where your local cluster is, reach out and find out where the next event is, and see if you can go along and engage the landscape locally and nationally. But yeah, reach out to your local cluster and find out who to speak to, and try and get along to some of the events when you can.
Great, thank you. Yeah, thank you very much for that. And hopefully anyone in the audience who maybe is new to clusters, or yeah, maybe they've been doing their own research, yeah, definitely connect in. Everyone's very keen to connect you in together. And yeah, you can speak to either Kim or me about that. And also, Michael, I just want to add, before we kind of drop off for our break very briefly, that there are a lot of people in the audience kind of agreeing with you. So, you know, we've got Esther saying that there's barely any research for radiation protection. So, you know, there is just a lot of things. So, of course, the sector, the area is still developing, still got lots of work to do, but really exciting to hear that we're on the right track and we've got you guys working.
Yeah, no, totally. And I'll just end by saying I can, you know, we talked very briefly about radiation. Most people that I've spoken to that have an interest in, let's say, human welfare here on Earth can find an application for their because we're still people in space, you know, we still have the same requirements, but in an entirely different environment. So things like medical evacuation hasn't really been covered either. Medical emergencies, operations, diagnostics in space, these are all things that might be very familiar to people here on Earth. These are all required in space, and you'd be surprised about how far behind that the human welfare research is when we compare it to the tech. We've got the tech to go to Mars, almost. We've got the tech to go to the moon. We could send people there very quickly, but what's going to happen to them when they get there? How are we going to get them back? How are we going to make sure they're safe? So these are all questions that need to be asked, and some of them may not have been considered as stringently as you think.
Great, thank you, Michael. I think that's a great note to end on there. You know, we've heard all about long duration space exploration, what's currently going on in terms of human health and space life support funding and further information, and where the gaps in technology are. So yeah, it was really great to speak to you here today, Michael. Thank you.
Thanks everyone for your attention, and all the best. I'll stop my share now. Cheers.
Perfect. Thank you. I'll hand it back over to Kim just now.
Great, thanks, Michael. Thanks, Christine. That was really fascinating. So we're going to have a short break in a couple of minutes before we move on to the next of our presentations. It sounds like there's a bit of a technical issue with my slides earlier, so I'm just going to share my contact details again on screen, and you'll be relieved to hear I'm not going to do my whole presentation, but yeah, just so you're able to contact me and find out more about the Cluster Builder project. Here's my email address and the address for the Bioeconomy Cluster Builder. And as I said, you find a recording of this session and all our previous sessions on there. you can access them after the webinar today. So yeah, we're just going to take a short break now. If we come back at 5 past, and then we'll move to Martin Dade Robertson's presentation at that point. So yeah, see you in a few moments. It's my pleasure now to introduce the second of today's speakers, Martin Dade Robertson, co-director of the Hub for Biotechnology in the Built Environment. Martin's going to deliver a presentation exploring the concept of space architecture, and then we'll follow a similar format to the previous section, where we'll then have an opportunity to put your questions to Martin and the wider group. So I'll stop sharing now and hand over to you, Martin.
Thanks, Kim. So let me see if I can share my screen here. Apologies that I'm I've had I'm gonna have to leave and come back.
Oh, it sounds like Martin's having a few technical problems there.
I'll just come online for a sec so you're not all
Yeah.
alone up here. I'm sure he'll be back in a
Yeah, let's have a
moment.
chat. Yeah, I think he said he was going to rejoin, so give him a couple of seconds to do that.
And also one thing I want to share to the audience is if you do have any questions for some of the panelists, if you forgot to ask it in the session or anything, then feel free to send them through in an email. And so I know Michael is keen to answer any questions that come through. We're just very keen to connect all of you in together. If you have any ideas to discuss with them or anything, yeah, please let us know.
Yeah, I'll just echo that, please. Yeah, we'll share our contact details again towards the end of the presentation. Yeah, please do get in touch.
There we
Hi.
Apologies. I've had computer issues all morning, and
No
then
problem.
it suddenly decided it needed to reset all my security settings. It's a brand new computer, you see. So here we go. Let me see if I can now save to share with you, and I'll get through extra quick to give us a bit.
No, you're good. You're good.
Okay. So let me share my screen. That looks better.
So I don't see anything yet. Ah, here we go.
Right. Yes, you will in a moment. Does that look okay?
All looking good. Yeah, I'll leave you to it, Martin. Thanks.
Thanks very much. So sorry again, sorry about that. So just just to say, part of the reasons for my discombobulation here is that I've moved institutions recently. So I was formerly at Newcastle University, and I'm now at Northumbria, and I've got to set up everything afresh. So it's a new computer and a new setup. Just to say that in terms of my affiliation, I was formerly the co-director of the HBBE. I'm no longer, because the Hub for Biotechnology in the Built Environment, the centre is shared between two institutions, Newcastle and Northumbria. Moving over to Northumbria means that I'm part of the Northumbria side, but I'm still very much involved and here representing it. Just to explain that my background is perhaps a little unusual. So I was an architect, or trained as an architect originally. Then I did my research, my PhD and my master's in digital technologies and their relationship to architecture. And then more recently, I segued into synthetic biology. I did a master's in synthetic biology, and my research looks at the applications of biotechnology to the built environment in lots of different ways, and the emerging field of biodesign. Just to give a sense also of the context that I'm presenting from today. So the Hub for Biotechnology in the Built Environment is a research centre that I founded, doing this, looking at applications of built technology in the built environment. We did not specify whether those were earth-bound built environments or indeed extraterrestrial built environments. And this idea of space architecture is definitely an emerging theme within the grouping. And I co-lead one of the groups, Living Construction, which is really to do with the way that we fabricate and make future building materials using biology of different sorts. And I'm going to hint at some of those concepts today. So we are a little bit involved in space research, not a huge amount, but I'm going to show some, just a little bit of a smorgasbord of different projects, which I think might have relevance or already do in different ways. Just also talk about my new institutions. So I've only been here now for just over a month. But Northumbria University is getting a reputation as being the sort of Northeast academic centre for a lot of space research now, and that's been cemented recently through the winning of this huge contract to build this Northeast Space Skills and Technology Centre. This is not something I've been directly involved in, but I think that space research inflects an awful lot of what Northumbria University is doing now, and the way it sees its strategy in the future. And so the things that we're doing are related, but there is a much broader community here. And indeed, there may well be people on this call who know about these initiatives and so on. We're talking from the northeast of England. I'm just wondering now, having heard a presentation from Durham, whether we should just move Hadrian's Wall a little bit further south, and we could all be in the same network and cluster, but we'll see how this goes. So I'm starting with this image, which was the introduction to my slide deck, really. AI generated, a ubiquitous AI generated images that I've come up with, that was inspired by really the opening lines of a grant that we were involved in, that was led by our friend and colleague at NASA, Lynn Rothschild. Lynn Rothschild is a senior researcher at NASA Ames, and really works, broadly speaking, on biotechnology and its applications to space travel, but had a particular interest, and indeed we connected through a particular interest in buildings and constructing things. And she started the grant with this couple of lines, really, comparing the way in which we currently do spacefaring as what a turtle does, right? So we carry our habitation with us, which is actually a very reliable way of having a habitation that we can carry and we can maintain, but ultimately isn't the way in which we should be considering space travel. And this is particularly true when we think of interplanetary space travel, where we're going to have to settle on set up colonies on other planets, and those colonies, we can't take all of the materials and equipment necessary to construct with us. The payload issues are just too significant. We can't take cement mixers and other things up onto other planets. So how do we think about that then? So our way of thinking about that is to say, well, if we're going to build on other planets, we need to do probably three things. I'm using the word build here broadly. So I'm obviously interested in the built environment, but architectural structures, but I think this is the way that we build anything. So any material object device that we need to create has the same set of parameters that we need to think about when we're designing it for these very tricky and actually for us, hostile environments. So one is that whatever we make must be able to make use of locally available resources. This is in space terminology. I've often heard it described as in situ resource utilization. So we need to use what we find at the places that we're going to. We also don't have the benefit of a labor force, so we can't imagine that we're going to send a bunch of construction workers over to other planets to build for us. So one way of thinking about this is that our structures will need to be partially or says of, should do that? Should say or wholly self-assembling. So they should be able to somewhat construct themselves or make use of other forms of assembly, robotic assembly, and other things. And then once constructed, the materials that we make are going to need to be capable of adapting to change in their environment, and basic issues, for example, of repair, the kind of things that we might on Earth easily throw away or just take down to take to some workshop or other to repair, are not going to be possible. So actually building materials which are able to respond, adapt, change, and ultimately repair themselves also is going to be very important. Sometimes this is within the biotech world considered to be a field called engineered living materials. So biology connects these things together, because if we look at the way in which biology constructs materials in nature, we find countless examples of the construction of biological materials and systems using locally available resources, incredible feats of self-assembly, self-organization and structure, and that capacity to adapt and change. So biology here is definitely at least part of the answer. It might not be the whole answer, but it is at least part of the answer to how we might go about this. So I'm just going to give a few examples of these three themes and little projects that might inspire interest or conversation as we go. So the first theme of in situ resource utilization. So We came to this, this was really before the Hub for Biotechnology in the built environment, and more recently, and the more recent projects that we've done with NASA, but we were asked to contribute to a special issue of the Journal of British Interplanetary Studies on how we might consider constructing buildings on Mars from a biotechnology standpoint. And I coined the term there, a radical vernacular, based on the idea, the sort of architectural idea of vernacular architecture, which is essentially architecture which uses its local resources and takes on a particular characteristic and form because of the utilization of those local resources, usually stones and locally available timber and other things that give our buildings a characteristic style. And we started to ask ourselves speculatively, well, what would the vernacular architecture on Mars be like? And at the time, we'd started working on microbial biomineralization. So essentially, and I won't go into the scientific detail of this, although we can talk more about this as we go on. This is a process by which microbes, in fact, lots of living cells produce or indeed induce the formation of biominerals. And this was utilizing a particular type of bacteria that creates an enzyme that subsequently changes the pH of its environment and then causes mineral crystals to form. And those mineral crystals, when mixed with an aggregate like a sand or indeed a Martian regolith, and we've done experiments with Martian regolith as well, cement. So they cement the material together, you get something akin to a limestone or a sandstone at the end of it. The image you see on the top right are some casts there, some small cubes, 5 centimeter by 5 centimeter cubes that we've made using this process. And we speculated using this process on a kind of smart assembly of cementatious materials, where we would try to get regolith, in this case Martian regolith, into inflatable formwork. We would then feed our bacteria over a period of time to create cementation in the formwork. We also have been working on intelligent cementation, so using forces in the environment to generate cemented form. And then for structures to be left, once the materials have been cemented, structures to be left that acts as a sort of the exoskeleton for inhabitation. The strange, weird, alien-looking things here were nothing more than a sort of aesthetic speculation, really, but they sufficed for the paper. So we've done a lot of work in this area now. So since that paper was published, we've had a number of funded projects to look at all kinds of different aspects of biomineralization, how we control it and how we feed it. I don't have time to go through all of those, but I want to just highlight one of our most recent projects because it's work that's not been published yet, but it's a concept we call solar cement. So fundamentally, we know that the microbes that are creating our cement are not performing a kind of magic. So they're taking energy and matter and they're converting that energy and matter into different structure and form, but they still need an energy input and they still need a material input in order to create the cement. So if we were to imagine deploying such a system in a resource limited environment like the surface of Mars, we have to understand in detail those inputs and outputs. One of the areas that we've been working on is the energy input. So currently our bacteria are fed on, well, we say they're fed on Haribos, they're fed on essentially glucose in order to give them the energy to reproduce and then to do the metabolic activity that we need to make the cementatious material. And so we've been looking at least of trying to work out how we can reduce that requirement on essentially agricultural products, which is what we're using to make our glucose source, and into something else. And in starting to think through this, we've been working with a group at Nottingham University and feeding our biomineralizing bacteria on cyanobacteria. So we're taking the sun energy, the cynos are converting the sun energy into then a food source that give as an input to our biomineralizing bacteria. And we've discovered that it works. So the biomineralizing bacteria like the nutrient input. And so it's one way in which we could imagine that we can use cyanobacteria as essentially the beginning point, essentially if we think about the food chain rather than a manufacturing chain, but meaning the same thing, the starting point for our food chain or manufacturing chain would be cyanobacteria that would capture sun energy, which we could potentially have in abundance on another planet, and then convert that, do the first set of assembly to create a nutrient source for subsequent biological processes. Indeed, that talking to my colleagues in NASA, this is exactly the kind of thing that they're thinking about as well, starting off with cyanobacteria as the beginning for any process that they work in. We call this concept solar cement, and we're actually seeking some funding to take this further now and develop it into a more fully realized system. So my second category is self-assembly, and I want to just focus on one area of self-assembly, using biology to self-assemble materials. So this is now very much a space informed project. So the solar cement project is really developed for terrestrial applications, but in this instance, this is a direct collaboration with NASA, a project led by Lynn Rothschild, a project looking at really whether we can use mycelium, which is the root network of fungus, as the basis of a construction material. So this is a big, quite sprawling project with lots of different elements to it. Some of them looking at scale up, some of them looking at how we grow, particularly in resource limited environments, the mycelium, and different constructional approaches, as well as ways in which you can architect habitation. So there are architects involved in it as well. Our involvement is via a PhD student, Monica Lipinska, who could frankly as easily be giving this presentation, if not more easily giving this presentation today, who has had experience, quite extensive experience in space research. And this is the images I'm going to show here are from her PhD, and there's specifically the chapter on self-assembly. And so it starts off with the idea that mycelium is a very good binding material. So if you grow mycelium on a substrate, it will bind that material substrate together. Of course, it needs a biomass input in order to grow. But what she's discovered is that it doesn't need a great deal of biomass to kickstart the process of mycelial growth. So she's been looking at experiments. The first image I'm showing you here are this kind of web of these roots, these fungal roots that are holding together, in this case, sand grains. She's also been working on Martian regolith simulant that actually it's able to grow and hold the material together with relatively little biomass input. She's trying to limit the amount of biomass input, because any biomass that we can create, say on Mars, for example, is going to also be competing with human needs for food and so on. But what's happening here is self-assembly at the micro scale, because these roots are self-assembling, self-organizing, and then growing through these aggregates. We can then think about the next scale up. She describes this as the component scale, where essentially what she's doing is imagining creating bricks made of these components. But those bricks are then, because of the way that mycelium goes, able to bind together once assembled. So if you put these bricks together as they're still growing, the mycelium continues to grow and actually fuses across the fuses across the bricks. In fact, the mycelial roots will grow into one another and fuse to create a very strong connection we call a biological weld. And we have a separate project at the moment that we're just about to publish on, where we've been assessing the strength of these biological welds and discovering that in some cases the welds are actually stronger than the material around them. So this is another example of a self-assembling then connection system. And then the final stage is to imagine how we might construct aggregates of these different structures. And she's been working on forms of brick that will allow for a degree of self-assembly, using a combination of interlocking parts that are then jammed. So rather than if you imagine a bricklayer coming along and putting these parts together by hand, we can essentially shovel them together. Because of their shape, we'll get connected in particular patterns and forms that will then hold and allow that welding phase to occur. So we have very minimal labor involved in creating the structure, and then once the structure is created, it will hold through those biowelds. And this refers to other methods that we've seen in construction design, including the idea of jamming forms that will hold together in particular wells after they've been constructed. So my third category in this very brief go through is the idea of an engineered living material, a material that retains its capacity for change even after it's constructed. And from here, we're going to go back again to mycelium. So the image here is an electron microscope image of this tiny fibrous network of mycelial roots. In this case, growing on their own, so they're not growing in any substrate. Well, they are growing in a substrate, so they're growing in a liquid media in this instance, but they're not growing to bind anything together. They just are. They are a mat of these roots. But what we can see here, if we highlight them, are these little nodules or seed-like forms, and these are spores. So they're effectively the seed form for the mycelium, and they allow the mycelium to preserve its DNA in stasis. So even after the mycelium itself is killed, these seed forms in certain type of mycelial species continue. And that means we can trade a material like this. So this is a mycelial leather. So this is a mat of many billions of these mycelial roots all grown together, formed into something that feels like a leather-like material. In this case, it's maybe a little bit more like paper, but it can be made to be like a leather-like material. So it can be then made into clothing or canopies or other sorts of fabric-like structures. But what we've done here is to punch holes in it. So this has been dried, it's been treated, it's essentially dormant. But here we've punched holes in it. And then what we do is to re-nutrify the hole. So we put some water and some nutrient into the holes. And that wakes up the spores, and then the spores regrow into those holes. So we have a self-healing material, which is for the time that its healing becomes metabolically active, but then we switch it back into its metabolically inactive state. We've been doing lots of experiments looking at the effect of this healing, and have discovered that quite often the healed part is certainly no less strong, and sometimes even stronger than the material around it. So that was quick, probably not as quick as it needed to be, but it was a quick run through some of the projects that might open up some ideas and interests that do have something to do with that might spark some interesting technical ideas, and all of these are projects that we're actively pursuing. Just to conclude, just maybe giving some thoughts from observations that we've made in working in our group so far, is that the amazing thing about biology is that it's capable of these incredible transformations of matter. And so it can create with very simple molecules, very complex molecules that become ultimately complex structure, that become complex material. And we don't really have any other engineering type system that can do that. So cultivating biology in this way gives us potentially new types of capability in resource depleted environments. But it is also true to say that biological matter is the one type of material we haven't found yet in abundance outside our own planet. And of course, thinking about biotechnologies means that we have to consider not only keeping ourselves alive, but the life support systems that are required for other organisms, whether it be microbes or mycelium, or indeed higher order organisms that we might need to support our interplanetary exploration. So this is clearly a challenge. There is almost a kind of mismatch between thinking about biological technology and the challenges. The other thing to say is that I really like this quote. Jamie Davis is an Edinburgh-based anatomist, and he's written books on developmental biology, and he describes biology as an alien technology. So attempting to understand biological systems and processes, we're often confronted with radical complexity, and so this makes these biological systems a real challenge to engineer. I just wanted to give, before completing, just a quick shout out to, this is work that is a sort of spin out really from the Hub for Biotechnology and the Built Environment, a group of PhD students. Monica Lipinska, who I've already described as one of them, set up essentially a research network called Biofutures, which looks at these questions of really speculative biotechnologies for interplanetary exploration from all kinds of different perspectives, from an engineering and science perspective, but also from design and creative arts perspective as well. They have a website which is just launched, and it's really interesting to go and see their work. So that's me. That's the presentation. Just to chat out. If anyone wants to follow up with me, my email is there at the bottom. I'm happy to take questions after the presentation as well. But I should stand down a slightly over time, as I always am. But that's what you get. Inviting academics to do these things is what happens, unfortunately.
Thanks, Martin. That was really fascinating, and yeah, just shows how the power of biological systems to transform material into the material we find where we're going into the things that we need, I guess. And a couple of questions have come through. The first is from Esther. Would you also consider cyanobacteria and fungi glue with regolith as a living construction?
Yes, absolutely. So it's interesting with the work that we're doing with Nottingham. So this is quite early at the moment. Unfortunately we had a grant application that we nearly got and didn't quite. But essentially anything that can glue regolith together is really useful. So one of the things that we've been thinking of is that as well as biominerals, particularly where you've got structure where you require some tensile strength, the capacity of different bacteria to produce polymers as part of their biofilm, and we work with a couple of different polymers at the moment, would be really interesting. So anything that can glue regolith together in ways that are fast and make a robust material are definitely going to be of interest. We've been focused on biominerals because this has been one of the major areas of exploration in biotech in the built environment for terrestrial applications, actually. But there are lots of other potentials, many of which we don't know about yet. And one of the things I think we really do need to do is build up a library of essentially microbial polymers that we can start to produce and work out what the right conditions are to produce them. Sorry, Kim, I think you're muted.
Thanks.
Yeah.
Thanks, Martin. Yeah, question from Michael, one of your fellow panelists. Where does using biological agents in creating surface structures sit next to planetary protection considerations around ISRU? Is there a way we can limit the lifespan of the organisms to prevent contamination of the planet's surface?
Yeah, it's a really good question. So this comes up a lot with Monica's dissertation, in fact, to the extent that she's written a chapter on it. I mean, so there are sort of philosophical and there are technical answers to that question, I suppose. I mean, there is certainly in a lot of I mean, in a similar sense, we have the same challenges with working with GMOs on the earth, right? So there are lots of contexts in which we couldn't deploy a GMO in the environment. And so we tend in our research when looking at the synthesis of new materials to imagine systems that will be bounded within factory settings or within containment of some sort, and then also engineering the organisms such that they require very, very particular additions to their metabolism that they won't be able to find in the wild. I suppose the more philosophical question is that it seems to me inevitable for interplanetary exploration that we're going to have to grow things on other planets, and that the level of control that we have of biological systems is always going to be limited by their capacity to evolve out of whatever situation we engineer for them. So I'm always a little bit suspicious of the pure technical solutions to this, and start to think, well, what we have to do is build our ethical guidelines about what we want and what we don't want to do. And so I think there's some real challenges there, and I don't know that there's a straightforward answer, to be honest with you. We can certainly put forward proposals which limit issues of contamination and so on, and escape from the biological situations that we create. But I'm not sure that we could ever be 100% on our once we go to other planets, we contaminate them, and I wonder where those limits are. This is not an area that I've researched very much, but it's one of the things that we did, certainly in Monica's work, that we felt was important for her to address as part of her thinking.
Great. Thanks, Martin. Just looking at the Q&A, we've got a couple more here. So from Mark, how much information is available around the detrimental effects of lunar and Martian regolith dust on both structures and life?
I don't know as much. So I don't know, honestly. So I haven't looked into that, but I'm not aware of the specific studies on it. Yeah, and I'm not sure what experimental work would have been done to allow that stuff to be worked out. But yeah, I don't know. I mean, I suppose there's a good rationale for consolidating those materials, right? Certainly, you don't want fine dusts and those sorts of things, but yeah,
Yeah,
I'm not aware of that research.
I think Beverly's question might be along similar lines, really. It's around how do you protect the material from radiation on a planet like Mars if they're still fusing together? So I guess that's a similar.
Yeah, so interesting. One of the sub areas that I didn't describe today is that we're working, for example, with bacteria that will be melanin producers. So we've been sort of concept sketching around developing melanin producers. So there are also types of fungi that produce melanin as well, which has some good UV protection capability. So we think there's an area of research into UV protection using melanin production. We're just about to publish on a bacteria that we've engineered to be an incredibly effective melanin producer, which will work alongside a cellulose producing bacteria. So we can produce essentially a type of membrane, polymer membrane, which is absolutely infused with melanin throughout its structure. Again, we've been thinking about that for Earth applications, but the UV protection potential of that might be quite interesting.
Thanks, Martin. Next question, has any work been done with cell-free manufacturing systems in space?
And I think there must have been. I think there must have been is the answer. I can't speak to that because we don't. My lab doesn't do much really any self-free. I know of a couple of collaborators at Newcastle and one or two at Northumbria who have looked at self-free systems. I assume that there must be, because it is an obvious way to go. Because in self-feed systems, you don't need to worry about the longevity of the organism, although self-feed systems are fragile in different ways. But not in our work yet. Most of the material synthesis that we do does require a lot of the cell. So it's quite hard to know how you would build like a cellulose pathway or the biomineralizing pathway outside the cell. So just the enzymes for biomineralization, for example, are very complex and multi-leveled. So even engineering within the cell is quite a challenge, but taking out that machinery and putting it somewhere else is not something we've attempted to do.
Thanks. So the next question is kind of, there have been bacteria found in extreme conditions on Earth, opening up the possibility of finding bacteria beyond the planet. Is there any consideration around trying to utilize this extreme condition bacteria for growing materials or habitats, or do they not have the right properties? I suppose it's a bit of a question within a question there, isn't it?
Yeah, it's a really good one and really interesting. So I can't speak for NASA, so I'm not NASA spokesperson, but their biotech team works alongside their extremophiles team quite closely at NASA Ames. And so they've been studying a lot of extremophile bacteria with two aims, really. One being to look at signatures for life. So what the obvious question with extremophiles work are what are the limits of certainly carbon-based life forms as we know it? What are their limits of what are their limits of life so that we know what to look for, what the signatures to look for are in other planets. But the other thing is to understand them because they do synthesize some extremely interesting things. And so some of them are used, for example, in the context of biomining because they're able to leach out different heavy metals and other things. We had an amazing conversation with one at NASA a few years ago on the really crazy chemistry that goes on within some of these extremophiles. They're very hard to cultivate and they're very difficult at the moment to imagine how we might engineer them. But I do think that there is a potential resource there to be looked at. The other thing to consider as well, we're very interested in microbial spores. And it's been shown that microbial spores some types of microbial spores can survive the depths of space, survive the vacuum of space and still be able to germinate. And I think as a storage and a mechanism for biotechnology, developing and engineering spores is a really important thing. And we have some ideas about doing that as well. At NASA, they worked on a project 5 or 6 years ago called the Hell Cell, which was to try to take the crazy capability of some of the extremophiles to survive heat, pressure, and other things, and to engineer a chassis organism that could be engineered to do lots of different things with this incredible capability to withstand the sorts of challenges that you might find in space. It was a part of an iGEM project, I think. So it was done as a team, and it was conceptually there. I don't know where that project ended up, but I know it's something that NASA are really interested in.
Thanks, Martin. Couple questions now, and then we'll move to the next speaker. But there are two more in the Q&A box here. I think to some degree you answered this question in your last response, but as fungi extracts minerals from substrate, would you consider using fungi for extracting minerals from regolith on the moon or Mars?
Yeah, that's really interesting. We haven't. We didn't think about that. We've thought about that with microbes because we know that there are certain microbes that can mine. And I know that NASA have got some projects ongoing on mining with microbes. It's really interesting actually because it may be that mycelium can grow in a way that it would perhaps be difficult to get the microbes to grow, and we certainly see them being able to grow through substrates. But no, we haven't tried to do that kind of research, so we've not seen that in our group. Thanks,
Martin. Just in the interest of time, we're going to move on to our final presentation now. Thank you. And we'll pick up on any questions that we've missed there as we go along. So, Christina, you've just appeared on screen. Did you have something you wanted to add there?
Oh, no, sorry, just getting prepped.
No, that's fine. I thought you were going to come in there for a sec. So, yeah, thanks, Martin. We'll move on now to our final speaker, Professor Derek Stewart from the Advanced Plant Growth Centre at the James Hutton Institute. And Derek's going to speak a bit about how controlled environment agriculture can be applied in space. So, Derek, I'll hand over to you.
Okay, thank you. Video seems to have been stopped from your end, so I'll just share the screen. Right, is that coming through for everyone?
Yep, all good, Derek.
Cool, okay. Right, so good morning, sliding into afternoon, everyone. So I'm going to do a kind of whistle-stop tour of what controlled environment ag may do in space, and actually look at the space-Earth interplay and how this has developed as well. So I'm director of the Advanced Plant Growth Centre. Kind of does what it says on the tin. It's around about a £30 million innovation centre based here at the James Hutton Institute in Dundee. Excuse me. And two of the pillars in that are controlled environment ag. One's broader environment, controlled environment agriculture, and the other one's vertical farming, which is basically three-dimensional CEA. And I'll kind of talk about some of the developments we've had in there and how they can be applied as you leave Earth. Let's contextualize the problems and why we're working on this. For us, it's looking at populations going up, climate change is becoming problematic, so we need more food. If you need more food, you need more energy, water, land. We can't grow any more land, so we're going to have to do something else. And the land we have is getting trashed pretty much consistently. So controlling our environment to grow food becomes a logical way forward. Climate change is getting worse. If you read the doom and gloom stories in the news today, you'll have seen that I think we've had the warmest year on record again. So things are getting worse. And by 2050, anything between 12 to 40% of the world's environments will be different. So our ability to grow is diminishing, but population is going up. Kind of good news on that, and this will slide it into the space bit, is actually the way we grow food is transitioning into a much more digitized approach. So we're using things like sensors, whether it's drones, space-based satellite sensors to look at how we predict cropping and how we use energy on land and using renewable energy to create usually vertical growing systems or controlled environment ag systems. The advantage for on Earth is that you can guarantee you will grow in that system regardless of what the weather or climate is like outside. And a lot of these things have come from space-based interventions way back in the long days of space exploration and the science that spun out from it. So one of the more classic examples is satellite-based systems and the analytical and optical systems within that, and looking at Earth mapping has been translated through into multiple different companies now selling these services that from the same scan, you can determine soil health, what the soil is like, the quality of the soil, monitor crop and weed or wild environment crop growth. You can then look at disease epidemiology and weed epidemiology, whether the plants need fed, and all of that kind of feeds into, and increasingly with AI systems, giving you yield prediction models. So this is turning agriculture into smart manufacturing, and the predictions from this are being sold on these stock exchange guys that are predicting prices going up and down. So the original space data is now underpinning significant levels of trading going on globally. Space development has also developed a huge amount of optical technologies and solutions that are feeding into the agricultural sector. And generally, it's the if I can measure it, I can manage it approach. Now, these are all getting enabled on Earth, and you would absolutely need them off Earth where you've got a lesser amount of people. So if you're growing in a controlled environment, whether it's on Earth or orbiting the Earth or on different planets, there are multiple different ways to do this. Some of the ways could be if you actually look at some of the films on there, and I'd recommend if anyone's not seen it, watch Silent Running. That's a great example of growing in space, or something that doesn't look too far-fetched. You also get a laugh as well. So there are multiple different ways to grow crops, and here we're focusing on the different vertical farming concepts. So the one at the bottom center is Intelligent Growth Solutions, highly successful company. Something's just come up saying start my video. Is people not seeing anything?
No, all seems good, Derek.
Yeah.
Yeah.
Zoom's obviously playing up today. Yeah, so there's multiple different concepts. You can make them as complex or as simple as you want. But increasingly what we're seeing is much more sensor and AI-enabled systems coming in. And indeed, bringing these sort of controlled environment concepts is bleeding into a lot of governments' approaches to agriculture now, because they're seeing to secure food, you need to have systems that will absolutely produce food, or not just food, but materials and pharma as well. And this is just a nice example from the German Agricultural Systems of the Future program. And you can see on the left, lots of indoor farming systems are programmed in, and different controlled ones on the right. So if we jump really abruptly now to space, there is a group set up run by Matt Gillingham in University of Adelaide that we're working with, and it's a centre or an initiative looking at plants for space, specifically taking the tools and tech we have on Earth and how can we translate them up and grow plants in space. And the thought for that is predominantly looking at plant and food redesign. So going back to some aspects of what Martin was saying about redesigning microbes, we can redesign the plants. But also looking back to Michael right at the start, he was identifying what the people's demands are and what they need, and how we then design biological systems that best fit into them. And so it's worth looking at the Plants for Space setup, because it is a pan-global setup that we're working as part of, predominantly from the crop side to work with. The graphics are kind of funky 70s things, but you can see even then the concept of having, and I think they're drawing here, is that stylized on-planet system. And it's almost like, I think it's a library folio system where you would grow plants. And these are actually in operation on Earth as it is, but there's multiple different ways to do that. But the hard reality is, I think, is if you're integrating plants into an already incredibly complex system, they're going to have to work with everything else. They can't be standalone systems. So if you've got something like the life support system that's set up, and you can see already how this is probably a very simplistic aspect of what it looks like. Michael could probably better comment than I can. But if you introduce plants into that, what's it going to solve? Well, immediately, Again, if you go back to the Martian, that's the obvious connection there. You can take the waste in the urine because they're high in minerals, nutrients that plants need to grow. You could take water from or fit plants into your water recycled route, either as filtration and cleanup systems, but also as plants need water. And also, plants by their very nature are CO2 scrubbers. They need that to eat or to grow, and they will emit oxygen. So again, it goes back into an integrated portfolio of systems. So the plant's not there to just do one job, it would do multiple jobs within that. And of course, at the very end, you produce something you can either eat, extract drugs from, or materials from. The other thing as well is actually to remember that the people up there and the astronauts will be humans. There's a certain therapeutic value to having plants in there. So even though they're ultimately going to eat them, there's a therapeutic aspect to growing them as well, because I think mental stability is a big issue that would happen up there as well. So there's other ways that plants could be fitted into, different stylized ones, and they don't necessarily have to be full plants. The plants could be growing materials to feed fungal-based bioreactors, bacterial bioreactors, or the plants themselves could be classed as bioreactors per se, whether it's in an orbiting system or whether it's in an on-planetary system. Going back, I think, to what Michael mentioned at the start, the impacts of being in space, says he as someone who's never been in space and came to this quite late. Long-term duration up there there are reports that identify certain problems anyway. And I think it's already been mentioned that muscle loss and possibly bone density loss is a problem. We can fight aspects of that by boosting the diet. So using these control systems, we can nutritionally enhance these systems. So what we need to bear in mind then is if we've got people up there and they're eating these plants or using them for something, we have to have them at maximum productivity. Now, biology and the response to light is very genetically variable. So here we have just some data we produced on 5 different plants. Now we've got basil, chives, dill, kale, and spinach. Unlikely you're going to be growing basil in space because I don't think that they're going to be wanting pesto pasta every day. But things like kale and spinach that deliver significant level of nutrients you probably might want to be growing. And you can see the variation on different types of lighting they get is huge on actually just yield. So that all has to be optimized. And that's kind of work that we would do on Earth that can then be shipped up. Similarly, what we've done on nutritional dosing, and that becomes very species and crop dependent as well, as we could grow them in high levels of, in this case, it was zinc, selenium, and vitamin B. And we can add things like nanobubbles as well to increase uptake. What we were able to show in some of these crops, particularly in things like kale, well, particularly kale, but also to a degree in some of the lettuces, was zinc and selenium uplift levels within the plant compared to normal by 16 and 40-fold. Now, if you're in high stress environments, your immune and inflammation system diminishes, and generally what happens is you'll lose zinc and selenium at high rate. So you need to boost that through intake, and we can do that by boosting these crops to do that. To boost these types of things is facile because it's the interplay of environment becomes really complex. So the amount of data that goes into generating just Earth-based experiments for consumption in human systems down here isn't trivial. So we're now straying into the area of bringing AI and sensor-based technology into controlling and manipulating these plants. And again, that's all fully transferable technology up into space. So, for example, a good example of a project we finished a wee while ago now with Innovate UK, one of our vertical farming partners, Intelligent Growth Solutions, and a company called Garden. They were sensor producers. So you look here, it's got different trials on one crop with different lighting regimes, and each line across the way is a specific chemical. So you can see the different lighting trials. You don't even know what they are, but you can see the different changing colors. As you change the lights, you change the chemistry in these. Now, to do that using standard lab analytical protocols would be a nightmare, far too costly, far too slow. So we're working to identify sensor-based technologies that can look at changes in these amalgamated parameters that identify the plant is going off normal, and that the data from this then feeds into the control system to get the growth system back onto normal again. And again, that has to be there. Otherwise, the amount of time you would need to grow these things and monitor them would just be astronomical. To bring it into perspective, if you look at, say we're growing one plant, right, we're going to grow, I think, potatoes in space, right? Almost everyone likes potatoes. So that's one line of potato. So say we're going to grow one from my institute, Hutton Hero, great, fantastic potato variety. But we're going to vary the light, the nutrition we're going to give it, the temperature we grow it in, the gas composition, and subsections from that. Pick 3 different ones of those. If you combine all these differently, you get 6.5 different combinations, which will produce a unique looking crop at the end. So you could see that the potential for manipulating the growing environment, let alone the genetics, is absolutely enormous here. So we need extremely well-guided and learning growing systems to allow us to get to an endpoint fast, to be honest. Again, going back to that figure of man lost in space, people get ill in space, and you need pharma-related treatments to get to that. So how do we do that? Well, plants, or actually biology, is a fantastic green factory that's being employed. And as someone who was a drug designer in the pharmaceutical industry many, many years ago, and was always interested in natural products, it's quite refreshing to see that coming back. And plants and actually bacteria as well, and fungi, they don't waste time making, generally not waste time making mirror images. So if you're going down a synthetic chemistry route using traditional chemistry, you'll make 2 mirror images often of a drug, unless you do some really expensive chemistry. But often 1/2 of that is either just a waste or is very detrimental. The classic example of that is thalidomide, where what we call an antimer, 1 mirror image was fantastic, the other caused massive birth defects. Plants don't do that. Plants will make the one image. They don't make the opposite one because they can't use it. It doesn't dock into their enzymes. So that's a great way forward for making it. Now you can do that in multiple ways. So you can grow it in the plants, as I've shown. Potentially you can use cyanobacteria, you can use more classical microalgae, and actually systems called Aquacell or the Omega Hub have already been designed and shipped up to be tried in space. And those systems have been well trialed on Earth and actually being used and exploited to develop different chemistries and outputs. Similarly, you can do the same thing with plant cell culture systems. Plants are it's a harder one to control in plants because they'll suddenly flip and start producing cell walls. And then you just got a whole plug rather than a distributed system exuding chemicals. There's actually a great example of that going on at the moment in Scotland. One of my mates, Gary Loke at University of Edinburgh, Gary's got a company called Green Bioactives that is using plant cell culture systems to actually grow chemicals. And if you've got a plant cell culture system, you can arguably go up into space with a bank of the different cells, a biobank, each for specific chemistries you want to start producing. And of course, what you can then do by having these biobanks is start to produce all these drugs in space. So morphine's the most obvious one. Something will happen and people will break legs, dislocate shoulders, things will go wrong. Ideally, you'll have childbirth in space, so you may have a need for drugs, pain relief up there. There's a whole range of these drugs you can produce actually from the same pathway. So you have the same an established growing set of conditions for the cell type you're growing, and each strain of these cells can be producing one of these different types of drugs. The other way is if you want to look at more complex drugs and protein-based drugs, which we can actually use like virus injection systems. So you inject the plant with a virus that's already loaded with the kind of genes you want. The virus takes over the plant protein manufacturing system and starts to produce the things you want. Now that can then be producing drugs that are edible or can be extracted fairly facilely basically in a NutriBullet system, for want of a better way. So there's quite fast, I say facile, there's about 40 or 50 years of work goes into this. These systems are up and ready for producing drugs or materials in space. So the demands for growing or using controlled environment in space are massive. I think the biology sides are pretty well done, and we're ready to export them up and see how they work in space. What's not been tested are things like the impacts of microgravity to any great extent. Does that offer potential or problems? The other thing about growing in space or off-world is that actually the exposure to the higher radiation may actually start to generate, because of mutation, new germplasm that may be useful back on Earth as well. So this going back to, I think it was Michael was talking about that, this two-way approach, I think, has to be built in. And if I'm honest, selling the science to do stuff in space as giving benefits back to Earth is often an easier win, if I'm honest. So more than happy to take questions about the potential of controlled environment ag in space from anyone, or any left field ones on the plant biology. Thanks.
Thanks, Derek. So many touch points there for agriculture and space. It's just super interesting, and interesting also to see the feedback to earlier presentations around health and the built environment. So applications there. A couple of questions come in. The first is from Atharv. I'm interested in the potential applications of biosurfactants in agriculture, particularly in relation to space exploration and habitation. Are you able to discuss any research or developments in this area?
Biosurfactants bit's interesting because I think actually, if you think about just on Earth, all the big companies that are wanting to use soaps, for want of a better word, if you talk about biosurfactants, they're wanting to get away from fossil fuel-based systems. So plants and biology-based systems have got a really diverse set of renewable / sustainable biosurfactants we can grow. They're easily, actually, I think one point is you can get the plant to grow them, make them, or they can be generated from the waste after you've taken out what you want from it. And perhaps, so a good example is if you've got bacteria and plants growing on in a bioreactor system or a controlled environment system in space, the waste from the plant that isn't eaten, or you've extracted what you want, can become a feedstock or can be secondarily processed by bacteria to generate something else again. So again, it kind of goes back to the interrelation of systems in a spaceship. I think there is no place for a redundant system or a linear system. Something has to be linked into another. The problem, of course, you've got there is if one thing goes wrong, does everything go wrong then? Because it's interlinked and unravelable. But yeah, I think there's loads getting done in that area at the moment. I would argue that probably one of the drivers or pushers would be Unilever, because they've said their personal care products, massive biosurfactant use, has to be fossil free by 2030. So all their suppliers are generating huge amounts of activity and innovation going into that. People like Croda in Hull, I think it is, Teesside, are doing a lot of that. So yeah, there's plenty going on there.
Yeah, thanks. Thanks, Derek. Another question, what are the main barriers or challenges that need to be addressed to encourage adoption and scalability of controlled environment agriculture practices in space?
The biggest problem on Earth is energy use. You have to fuel the box. Arguably, if you're on space and, well, the further away you get from the sun, the less energy there is. So how are you going to fuel that? Are you going to take a nuclear reactor with you? How are you going to, I think someone else was talking about energy use. Maybe it was Michael or Mark, I'm not quite sure. Energy is at the back of everything you would need to do there. So the further out you go, the harder it's going to be. If we convert cosmic damaging radiation or downscale radiation. So for example, a good example of that is they're developing glass houses now that they've got downscaling films on the glass that the UV comes in, gets energy downshifted into visible light that the plant will much more sensibly use. Can we do that for other radiation so we can downscale that energy into visible light, or energy that can then go into battery systems that can then be used to, when it's needed, grow the food, when it's not needed, treat the waste. So again, I think it's energy harvesting has to be a key point there.
Yeah. Okay, thank you. Another question here, what ethical considerations should guide the use of biotech in controlled environment agriculture? It's a bit of a deep one there to throw in, but
no, I think I would say that's been the talk of the day since we started transforming things. It's interesting that if you look at a lot of crops, what has been bred would no longer pass through novel foods safety regulations now through traditional breeding. We tended to get, I mean, what comes out of breeding now does, but previously there were problems. It's all cost benefit and use and benefit analysis, I think. We've seen the migration from genetic modification to gene editing now. And I would arguably say they're probably one of the most, certainly GM, and I was in multiple EU different risk assessment projects. It's probably been the most highest risk assessed approach to anything I've ever seen. So the tools, technologies, and processes are already there. And they're open for everyone to use. I don't think that's so much the problem. It's the ideological process of people thinking, rightly or wrongly from their point of view, are you being God and changing things? The gene editing bit's a bit closer because it's mimicking what mutations happen. And actually, if a gene edited organism comes out now, there is no way you can detect whether that's a mutant or where it's been created. So actually, at that point, ethics is more on the tools and technologies rather than the do you create it? Because if it's out there, you have to know what the background to that is before you can get it. And I'm sure that will happen. I'm sure we will see mutant crops coming out, but there probably have been gene edited, generated, but in a hidden format.
All right. Okay.
Yeah.
Yeah. Thanks, Derek. Unless anyone has any further questions for Derek, I think we'll wrap up there. And I'll hand back to Christina, who has a few further comments. So thank you, Derek.
You're welcome. Good to speak to you.
Lovely. Thank you so much for that really interesting presentation, Derek. I know I had a few questions, so I will maybe ping them over to you in an email. I think would be really interesting for the audience to know. But yeah, I am just, thank you so much for such a fantastic event, and thanks to everyone who joined in today. Yeah, we put a lot of thought and effort into bringing in the speakers, and just wanted to really bring to light some of the really interesting research and activity that's going on all over the UK, and how we can tie that into biotech. So yeah, thank you so much. I know Kim's going to do a proper wrap up, but I just wanted to say to everyone that next steps in terms of my work with Space Scotland is we'll be hosting 2 more biotech meetups. And so the content of those kind of meetups is yet to be determined. So we'll be using some of the conversation from today and hopefully also your feedback from attending the event to help shape these sessions. And so you should hear news about that over the next few months. But we'll send out a little wrap-up survey and just see who's interested in next steps, and also send out the link to anyone who might have missed the sessions or wants to go over some of the content that was touched upon during the presentations. I think that's everything from me. So Kim, I'll hand it back over to you. But if you want to contact me, I'll pop my email in the Q&A here. But I think all of you probably received numerous emails from me right now as of today, just pinging out the link and everything. So probably know it already. So yeah, Kim, over to you.
Thanks, Christina. I'll just share one final slide with both our contact details on there so that you can pick up with us if you have any questions or anything you'd like followed up. So yeah, really just thanks from me to all of you for joining us, to all of our great speakers today. We've covered some amount of topics, and it's been really, really fascinating to hear both the presentations and the questions that we've had put to our panelists. And thanks also to everyone who's, as Christina says, thanks to everyone who's worked so hard to pull this event together. Please do get in touch with either of us if you have any questions. And as Christina said, we'll think about follow-up activity from here on in. So thank you and enjoy the rest of your day.